Okay, hi everyone. Welcome to this new session in Arabic JUG. مرحبا بكم جميعا. This presentation is also going to be in English. We're looking forward to Arabic presentations in the future, but for now we have this presentation, this wonderful presentation about Project Loom. Before we get started, I just want to say that if you are watching this live, feel free to ask your questions on the live chat. And like if you have questions, I will try to forward them to Bazlur here at the end of the session. So we have Bazlur here. Welcome, Bazlur. Thank you for presenting to us. I know it's a bit early in the morning at your time. So you're based in Toronto, right?
Yes, that's right.
Okay. So it's like I think 6 or 7 hour difference. This is the nice thing about remote presentations. You can get to conduct interviews in this far away. Imagine if we hadn't had this remote
Right.
presentation. You would have to travel like I don't know 20 hours by plane to come
I never been to.
somewhere.
I never been to. You are situated in Beirut,
Yeah,
right?
I'm in Beirut, yes, but I
I have
have
never
a
been.
few others in other countries like Morocco or Egypt. Yeah, so
I have never been to Beirut, but I'm looking forward to. I would love to visit someday.
yeah, we'd love to have you. So this is the nice thing about uh, like remote sessions. So Basler is a Java champion, and I've actually read some of the articles on, I believe, Fuji. Uh, Maybe you can introduce yourself, Basler. You can go ahead.
Sure. So yeah, I have a slide for that, but I can quickly, uh, introduce a bit. So as you can see, my title, the title of this talk is "Creating Million Virtual Thread Using Project Loom to Improve Throughput." So I'll probably stress on a bit on this. So I'll moving on. I'll definitely talk a lot about it. Stay with me. All right, so let me give you a small introduction about me. Like Mahmoud introduced me, I'm a Java champion. I've got this title recently. It's a nice thing. Apart from that, I'm a senior software engineer. Work at Contrast Security. I'm a Java user group leader, Bangladesh. Apart from that, I also write. For example, I write on Fuji.io. If you want to get all things about Java, especially OpenJDK, you should definitely look into that site, which is fuji.io, which means Friends of Java, Friends of OpenJDK. Sorry, Friends of OpenJDK. So you should definitely look that out. Apart from that, I also write on InfoQ, the DZone, all those places. So that's a small introduction about me. Um, all right, so let me go into the agenda. I mean, that's the whole thing. That's the thing we are going to spend time on today. All right. So before going into the main topic, I mean, obviously it's going to be a virtual thread. Let me give you an so what I'm going to do basically, I'm going to set a stage first. I mean, before, as you can see, there are certain rules and agenda we say before going anywhere, right? Even though if you want to board on a plane, the attendees will say something, do this, don't do this, something like that, right? So these are the uh, simple what do we say uh, what I'm basically essentially what I'm going to do in this talk. So I'll briefly set a context, so basically setting the stage for the virtual thread so that virtual thread can come and then do the dance. So that's the idea. And then I'll talk about a bit about if that makes sense, and if there is any limitations available for are there sorry is there any limitation of virtual thread. So that's all. I mean, it's not going to be a deep dive. It's more of an introductory high level talk, so hopefully everyone will be able to catch it. And one more thing is, if you have questions, feel free to ask anytime. Anytime is good. I don't have problem. I'll definitely try to entertain as much as I can. But if I don't know, that's also okay. That will give me an opportunity to learn that thing, and later maybe some other way I'll able to answer that questions. So that's the agenda. All right. So moving on. Okay. So first thing is, what is thread all about? What is how Java concurrency is built on, right? So if you can say that, which is Java is made of thread. Um, the reason is, whenever you start a Java program, you'll see it has to it run by a thread. So why not I give you a quick example, short demo, and then I will start the presentation from the slide. So as you can see over here, I have a class. It doesn't do anything yet. So it has a main method. Let me remove. Okay, let's skip that. So the method starts from here. I mean, whatever code we put over here, it's going to be executed by something, right? Something gonna execute the code I write over here. So let's say I write hello world. This is a code. This is a statement that I'm going to expect to be executed, right? So let me say if I run this is going to be executed, and the question gets to be who execute this. So the answer is, we can even find out from here. So if we call this method current thread, um, if I run this, I'll see the output over here. The output is thread, whose name is main, right? Ignore all the other string for now. Just concentrate on main. So basically, what happens is, this portion of code from this curly brace to this curly brace is executed by a thread. In reality, Java, all things in Java are executed by a thread. I mean, it can be run. We can run multiple threads, but a thread is responsible for its specific job. So so that's the idea. So that's why we call it Java is made of thread. Anything we write is going to be executed by a thread. And from the day zero, I mean, from the early stage, like 27 years ago when Java was born, they introduced Java, and that was the one of the reason for being popular. I mean, it's still relevant, right? And still we're talking about Java. So that really helped to shape the Java. All right, so we can call it the execution, like this is the execution, right, from this curly brace to this curly brace. So this is the unit of execution. You can say that this is a unit of code that we want to execute, and it is executed by thread. So we can justify this statement, which is thread are unit of execution in Java. So that gives a interesting idea, which is, that means if we have more threads, which basically entails that we have more execution environment. And when we have more execution environment, that means we can do more things simultaneously. That's interesting, and that's probably we want. And if we have more execution environment in a program, that means a lot of independent things we can do simultaneously. Not necessarily we have to have everything independent, but certain aspect of or certain unit of code can depend on some other things, but that's okay. For the argument sake, think about if we have a lot of execution environment, we have a lot of individual or independent things running simultaneously, and that's interesting. So let's go to the next slide. So I mean, it's just I mean, whatever I have just said, uh, that's what it demonstrates over here, which is Java has all sort of layers where we use threads. For example, you know any code we execute is going to be executed by thread, and then if we need to translate exceptions, threads are the means of getting the stack trace. We have thread locals, we have debugger, profiler, all of them are involved with threads. So from these two slides, you can derive that conclusion. Thread is something that we need to know, or thread is something that drive Java. So moving on, now the question gets to be, like I said, we are gonna set an in stage first. So I'll definitely talk about a little bit how do we create the traditional threads. So let's get back to the IDE again. So like I said, whenever we call a main method, it's executed by a main thread. So we don't have to do it. We don't start main thread. It is automatically started by the JVM when we start an applications, but we can start multiple threads from here. So the easiest step of creating a new thread is basically this thread. Sorry about that. New thread, right? And if we pass any code over here in means as a means of runnable or lambda expressions, whatever we prefer, it's going to be executed by this newly created thread. So let's say I want to print over here, um, welcome to Arab JUG, right? So that's a statement I want to execute by a different thread. So that's the code I'm gonna put over here, and I'll have instance of this thread. Let's say thread, and then I'm gonna start it, and I want to wait to finish that. So I'll call join. So if I call it, you know, this is executed, right? You can see the output over here. Now, if you want to know if it is which state executed this portion of code, I can definitely print another line over here, which is call system out dot print length dot current thread. This is a static method that specifically prints which thread I'm currently running on. So if I run this method, I'll see, that's a different thread. That's a different number of thread. I can name it as well. If I don't name it, then it will, it will name like incrementally thread underscore 0. So if I want to name it, I can definitely set a name. Let me name it brand new Arab JUG thread. We can name something. We can name anything, in fact. So as you can see, the name appears over here. So that's a new thread, right? So traditionally, this is how we create threads. Okay. So one thing we have to keep in mind is that when we create threads in Java, it doesn't mean it's a Java construct. What do you mean by that? It means basically is operating systems essentially manage all these threads. Operating system create threads in Java layer. It is a thin wrapper. When we call when we call new thread, we create an instance of new thread and start. It basically call a native method, and it asks operating system, give me a thread. I have this set of codes that I want to execute. Give me a thread. So basically, operating system gives us thread. Java doesn't have a a, a construct of thread of in of itself. So operating system gives us the thread. So whenever we create threads, basically it's an operating system that we have to keep that in mind. So essentially, when we call Java threads, basically it means it's operating system threads or native threads, whatever name you can call it. That means that the thing. All right. So now that we know that, we established that it's an operating system thread, and it's an expensive operation because Java doesn't create thread, like it's asked operating system to create a thread, and the thread dot start considered inefficient. That's why, and it takes around 2 MB of memory outside of the heap. Let's say you have a computer with 8 GB memory in it. Now you have a Java program that takes like 4 GB of memory as a heap, and then you have available like 4 GB, right? Those 4 GB is going to be occupied by other process, operating system process, like all those things. And also, if you keep creating threads, those threads will take extra 2 MB of memory from those extra memory. So you cannot create a lot of them, and that's a problem. So like in the beginning, in the beginning of the slide, so first slide, I said we're going to create millions of threads, right? So now it seems contradictory, right? We cannot create essentially a million threads because we are out of memory. So if you want to create 1 million of threads, that's pretty much required 2 terabyte of memory. That's a huge memory, and probably we don't have availability of that much memory. And the other thing is, even though we create a huge amount of memory, if we have a huge amount of memory, let's say we create a huge amount of thread, there is a um, uh, cost associated with context switching. So operating system scheduler is going to give a particular thread a portion of time, right? And then let's say it depends on a algorithm of operating system. Let's, for the argument, for the discussion, let's say it's a round robin. So if we have 8 thread, operating system will give them everyone as a chance to execute based on priority. Some operating system ignore priority, some does, but let's forget about priority as well. Let's say everyone has the same priority, and so if we have 8 thread, eight of them is going to get sometimes frequently on a round and robin fashion. So if I have millions of them, that means you know so thread scheduler is going to be very busy scheduling all those 3 threads, and some thread will get, everyone will get less chance to execute their code. So in turns, even though we can have a lot of, theoretically we can have a lot of thread, if we have enough memory, the context switching is going to hold us. So we are not going to get a huge performance out of it. So we are sort of bound, limited by the number of thread we can create. So now the problem is, so that's a one limitation, right? The other limitation is, let's say we have a more modern web, think about modern web applications. So what happens is, let's say we have applications and I want to I want my application to use by as many users as possible, right? So a lot of users will come, as many user as large amount of user come to my website, my revenue goes, right? So that means I want to get a higher throughput. So now the question gets to be, how can I get higher throughput? In general, in our modern applications and modern web applications, when a user request, user send me a request to a web server give a thread to serve that particular request. So let's say I have a 100 threads allocated in my web application. So that's many thread I can allocate it with the memory and availability of my resources. So at a point of time, that means I can only serve 100 users, but I definitely want to serve 1,000 or 2,000 or more than that. If we have, that means if we have more threads, we can definitely serve more users. That means we can achieve more throughputs. The problem is we are limited by the number of threads. That's a problem. So over here, in the previous slide, we saw that threads are expensive. We cannot have a lot of them, because of their expensive. And over here, we see if we want to achieve high throughput, we are also limited by the number of threads because we cannot have a lot of them. So so that means that's why we do all sort of other things. And for example, we have a lot of machines, right? Let's say one machine can handle 100 through 100 throughputs, and so if we have 10 machines, that means it will be multiplied. That's why we use a lot of machines. But let's say if I have a machine with the same amount of resource, if I could increase the throughput without doing anything, that would be awesome, but we cannot do that. And the other thing is, our operating system in fact allow to create a millions of concurrent connections through the socket. That's available, but the problem again boils down to the thing that we don't have a lot of threads. So that's a limitation. Now, what do you about? I mean, there is a solution. There is a certainly we are achieving high throughputs in many web applications. So we go around with this problem with something else. Some use reactive programming, some use other things, other technologies, other frameworks, and some use just some expand their resources. For example, they multiply the number of machines they are gonna use. So those are solutions. But again, we are not in a way solving this problem. So we're going around with the problem, right? So now let's think about it. What can we do about it? Okay, so I'll discuss about that, and now let's moving on into the next slide and see in reality how many thread we can create in our operating system. That's an interesting experiment we can do. I mean, whatever I have said, you have to reproduce, right? So if you want to reproduce, what we can do, we can just write a code and see the output. That's the best way to justify a statement. So yeah, that's the code that I have written on my machine, and I was able to create 16,000 threads because I have a 64 GB of memory. That's allowed me to create this much of thread, and after that the JVM crash, and you got out of memory error. So you can try out on your machine. Just copy this good code and see how many thread you can create. So again, so basically this one is justify my previous statement, which is threads are limited. We cannot create as many as we want. Although if we could, it if we could achieve our throughput count, which is an awesome thing. But then again, it's an expensive thing. So we are limited by the number of thread. It's an expensive resource, all sort of things. All right. So this is basically same idea what I have so far said. This is the description of our modern web applications. So we have applications, we have a number of threads over there. We create pools of thread because takes time to create a new thread, and we cannot control how many threads we want to create, right? So what we do is essentially in web applications, we create a thread pool. Let's say we allocate a number. We set the number by tuning up, trial and error. So all those things, and then let's say we figured a number. Let's say it's a 400, and we create a on the startup, we create a thread pool that has a 400 threads running constantly, and then we get a request. We allocate that request to a thread. This particular thread basically do all sort of things to serve the particular request. So if we have 400 threads, like I said earlier, if we have 400 threads, that means at a certain time, at a point of time, we can serve only 400 requests. Given that this thread doesn't given that we don't have other things, it's a simple request response, and in between there is nothing. So all right, so these are the problem so far. Now that I have said this stage, let me know if you have any questions so far.
No questions so far. You can move on.
Okay, all right. So no problem. All right, let's move on. Moving on. Let me go to the next slide. Okay. So this is basically demo I wanted to show, but we can we can skip that. I will just describe it. Basically, it's a single threaded web application server. It's a very basic of application server that we see in our modern web applications. It just it waits on a server socket. It open a port 808 and then wait for a request. So if we send a request, it will just handle. And we don't have anything over here in this code. It can be anything, and it's a single threaded web server. Why not I show you the code? That would be awesome, right? Let me see if I have that over here. Okay, so let's forget that. So this is an applications that so wait on a server socket, which is port 808. Any request we give over here is going to accept by the server socket and then handle. The handle method doesn't do anything. It just, whenever it gets a text from a client, it just send it back. You can say it's a echo server. So let me see if I can run it. Looks like we can run it. So what I'm gonna do is, okay. So what I'm gonna do it is telnet, right? If I telnet, if I write anything over here, it just echo back with the uppercase letter. That's all it does. So it's a single threaded web server. It doesn't do a lot of things, and it's not even super useful. So the reason is, if we create another telnet client over here, you can see if I try to telnet and if I write over here, I don't get any result. The reason is, it's a single threaded server. It can handle only one request at a point of time, right? So now if I kill this tel client, I immediately get result over here. So because that client went away, now it can serve these users. Okay, so that's awesome. And but problem is, it's not super useful. And so what if we turn it into a multi-threaded web applications? What do we have to do? We have to we can create a new thread each time I get a request, right? New thread like this, and I'll move this handle method over here, and then I call start. That's all I need, right? And if I run it now, let's kill it and rerun it. So what I'm gonna do is, I'm gonna do telnet again. Hello world, hello Arab JUG. So I get response instantly, right? Now, if we want to connect another telnet, let's see. And if I type over here, I get response as well. So basically, two requests. I send two requests, and there is two threads, working on, serving these two requests. So that's awesome. So that means that if I want to, send a bunch of requests at a time, we'll be able to get response as well. So that's interesting. The problem is, now remember all those problems we had earlier. We cannot create as many threads as we want. That means we send like 10,000 requests, or 20,000 requests at a point of time. This application will crash. So that's the idea. And I have a simple what do you say, simple client application, which is, I call it DDoS attack. So what I did is, I created 20,000 socket, and then send requests to that server simultaneously. And you will see, you will get it as a, like, it's connecting, and after a while application will crash, because that this program, right, this particular program, whenever we get a request, we'll create a new thread. So that means 20,000 requests are going to try to create 20,000 threads, which is not possible with this resource available in my computer. So it definitely, the server will goes out to crash, and we'll see out of memory exceptions, all those things. That's a problem. I'm not gonna try this program running over here. The reason is, then this streaming will be interrupted. My I don't want to do that, but you can definitely try out and see the result. All right. So this simple problem can be solved with with the limited with a small change. All right. So over here, you can see I have created a new thread every time whenever I get it. get a request, right? So probably in reality we don't write code like that. We want to create a pool of threads first. So what we would do is, let's say I have a you know there is a thing called executors, right? Let's say I have a executors over here. I can create a new fixed thread pool, or I can create you know executors new fixed. Let's say we create a new fixed thread pool, and we allocate 100 threads over here. That means whenever we're going to run this program, we are going to create this number of threads, and it's a pool. So we're going to submit this task to this pool. Submit. Same thing, but this is how we do in production, because it's more controlled, right? And because we can tune thread pool, we can put number on it, so that that means right now we have like 100 threads in this thread pool. So we'll able to connect 100 requests at a point of time, and then if we have more requests, will the that doesn't that will our server will receive the request, but we have a 100 threads available at this moment. So 100 thread will be working on serving the first 100 request, and the other request will just wait until they finish. So there is a less chance to crash the application server. All right. So now the question gets to be, what if I want to run this DDoS attack? Again, this is going to fail. So how do we solve it? Well, that's where the interesting things that's coming to our Java, which is Project Loom, and I'm super excited about that. Okay, so sorry about that. So we can solve this problem by changing one line over here, which is new thread par. Sorry, this line. New virtual thread task part executors. So we don't need to put any number over here. So we're going to get a thread pool. It's not a thread pool. So let me rename it. It's not thread pool anymore, because virtual thread doesn't create thread pool. But the idea is, now if we want to submit the task, we'll get a new virtual thread each time we get a request, and mm, and this virtual thread is going to handle this particular request, and we can create a millions of them. Okay, that's a statement. I'm going to prove it. Wait a minute. So what I'm trying to say is, if we have a production code, something like that, we use executor service, and we submit task, we can just change one line over here, and that's it. We get all these benefits we want to have. The problem that we so far we established in last 30 minutes are going to go away, changing this new line, which is new virtual thread for task executors. Isn't it amazing? So there is a question over here. Let me take that. Hey, Mahmoud, can you bring that question to the screen so that?
Yeah, sure. So
Yes, the question is,
this is the question.
does virtual thread need adapting up applications code running on server like Tomcat? So my answer is, when the virtual thread is in JDK, it's still in preview mode, right? We are still experimenting. It's still under actively being developed. So once it is tuned and everything, it goes to the JDK, without preview feature enabled, then probably yes. And I'm really looking forward to have this. All right, so that's amazing, right?
Yeah, this is the only question we have. Yep.
All right. So moving on. Um, so what essentially I was trying to say, that all the problem that I have described so far, are going to go away with this new model of threading, which is Project Loom. So now, the rest of the presentation, I'm going to speak about Project Loom. So I need to, establish the establish the stage first. Why we need, Project Loom. So that's what I did. Okay. Even there is another question over here. Um, Mahmoud, if you want to bring it over here, I remember someone already ported Tomcat Thread Executor on top of virtual thread. I mean, a lot of other people are doing those all sort of experiment. So it's likely someone did that, and they're trying to see the result, obviously. And I don't know if it's going to be in a production thing yet, but let's see and wait. I personally would love to see that in near future, but it's not there yet. That's what I know so far. All right. So moving on, like I saw, I just showed you the code, right? If we have uh, this new line, if we change this new line, although all those problem we had goes away. All right. So okay. So now that we established that, and I want to show you a quick demo before I go into Project Loom, how it works and how it is developed, all these internal things. I want to show you a quick demo which I like. So this is the demo. So I copied this demo from a website which you probably know him already. Let me bring his site over here if I can. So if you want to read this article, go ahead. It's a fun. It's a really great article. So title is Gazillions Virtual Thread. The code I just copied from here, and I like him, which is Hans Kabuts. Maybe you invite here to talk in some day. He is really nice guy. If you invite him, he will definitely love to speak to you all. All right. So if I run this program, what essentially it's going to do is it's going to create a millions of virtual thread. As you can see, so first time it creates 1 million, and then it goes on creating 12 million, and it keeps creating. You see, over here it creates like 22 millions, and it keeps on creating. So it's interesting. I mean, it's creating a lot of virtual thread. At the same time, it's also uh, so here's the thing: does that mean we really want to would really be able to create like 45 millions of thread? Probably not at a point of time, but we can keep creating virtual threads. And when so the idea is when we write a concurrent program, right? We give a runnable to it and task. We give a task to a thread pool, and thread pool execute that task, and the lifetime of that task goes end there. So you can think virtual thread as like that. You give a task to a virtual thread, it will create a virtual thread, it will execute, and then it will die. So and then it will be garbage collected. So that's why we can keep creating millions of threads. But again, the statement of my presentation, which is we can create a millions of threads, that justifies this demonstration. All right. So let me drink a bit of water. All right. So the idea is, so now that we have established, virtual thread, which is, under the Project Loom, is going to solve a lot of our problems. So how, Project Loom works. So before going into that, it's a declaration, which is, it allows us to create millions of cheap, lightweight virtual thread. And now that we have a new kind of thread, which is virtual thread, we can. Does that mean we are going to remove all the traditional or classical threading model? The answer is no. We're still going to keep those. We're going to still keep that. Model, which is classical. We can call it classical threads. We can call it. We can give them all sort of names. We can call them platform thread, we can call them carrier threads, native threads, classical threads, and there is other kind of thread which is virtual thread, and we can call them virtual thread, or we can call them user thread, whatever. That's two names are basically given. All right. So now that we have two kind of threads, so we just have to keep that in mind. All right. Moving on. Now the question gets to be how we are gonna create virtual threads. So that's what I'm gonna show you over here. So I'm going to remove this code for now. So creating virtual thread is pretty easy. You know, we have to call thread dot start virtual thread. That's one way of creating virtual thread, and we can pass anything over here, and it will be executed by this virtual thread. Okay, so if I create a new, use this method start virtual thread, I'll get instance. Interestingly, this instance is basically a thread. So virtual thread in a way extension of our regular thread. The only thing is we can not create virtual thread directly using new instance. For example, traditional thread we can create new thread. That's something like that. But for virtual thread we cannot do that. It gives us few factory method or useful method which is called start virtual thread, and it will create a virtual thread. All right. So if we call thread.start virtual thread, immediately it will start, and whatever code we put over here are going to be executed by this virtual thread. So again, we can put a code over here. Hello world, and we can try to see if this is indeed a virtual thread. Thread.current thread. Now that thread started, let's wait on it so that it gets finished. Okay. If I run it, as you can see, it says virtual thread, and there are certain things over here. Let's ignore for now. But again, this line it proved that this is indeed this code is executed by a virtual thread. So that's one way of creating virtual thread. There is another way, which is thread dot of virtual, and then we have two options. We can start a virtual thread immediately with the start method, or we can get an unstarted virtual thread, which is the same thing. We'll get we need an instance. So let's say over here, example of unstarted virtual thread. I guess okay. So we need an instance over here. I get an instance. So that's example of, sorry about that. Let's call it thread one. Okay. So this thread didn't start yet. So if we want to start, we can just call it start method. That's all. But if we call it, if we call start over here, then this thread already started. And if we call the start method again, it will definitely give an error. So let me try it. So as you can see, already started. So it throws an exception. If we already start a virtual thread, we don't call it .start method. That's a two-way. That's another way of creating virtual thread. And there is another way. That's probably we're going to use in our production code when we're going to use them in our production code, which is like this. So for executors new not new executors new virtual thread per executors. So this is how we're going to use, because the reason is we have a huge amount of code already written using these executor patterns. So we want to just change one line over here. That will we don't need to do anything. So executors submit. So whenever we submit something over here, we will get a virtual thread, and this particular task is going to be executed in a virtual thread. So that's interesting. So that's a three way of creating virtual thread. And there is another interesting addition that I definitely want to share, which is now that this thread has a factory method, thread.virtual.start, maybe it makes sense for these traditional threads to have the similar factory method, which is off platform dot, and we can have started and started similar fashion, which is, this is going to create a traditional, sorry, not of virtual, it's going to be of platform. Okay, so this is going to be traditional threads. This is going to create traditional threads like we used to create last 27 years. It just it gives us a new factory method. It's a build based on builder pattern, and I like it. I like builder pattern, so you can use if you need to create traditional threads, you can create this way. That's a nice addition to the JDK. So any questions so far? Okay, if we don't have questions, I can go ahead. All right. So, all right. Okay. So now it's still under preview feature. Since uh, it's available in 20 as well. If you want to try it out, the JDK 20, you can definitely do that. But it started with JDK 19. And since it's a preview feature, if you want to run this program, you definitely add. For example, if you have a code that use virtual thread, you definitely need to use these additional flags to compile, which is enable preview and then release 19. And if you want to run them, then you have to again use enable preview. So also you can use this the third one without compiling first and then running. You can do the third one with one command, and also you can use JShell. The bottom line is you have to use enable preview to use all those features. So whenever I'm running this code, essentially I also enable those over here. As you can see, I have enabled preview over here. That's why I am able to execute this program. If you remove that, I won't be able to run those things because virtual thread is still under enable preview. And if you go to the source code, probably I can show you. I'm not sure if I can show. Yes, as you can see, there is a line over here which is preview feature, and feature name is virtual thread. Okay, so since it's a preview feature, we have to enable preview. The reason is it's under preview, so that we unintentionally, or we cannot use in production applications. It's a blocker because it's being actively developed still, and as a developer, our responsibility is to give feedback to them if there is any, and if we face any problem. Okay, so moving on. Now the question gets to be how this virtual thread works and how it is developed. So that's the uh, essentially a high level nitty gritty. Probably we are not going to go in depth, but I'm going to give you some idea how virtual thread how virtual thread works, so that we understand how we can achieve million threads, right? I mean, it's not just a magic. All right. So virtual threads, are built on two concepts, which is continuation and scheduler. I'm going to talk about continuation in a second. And so what happens is virtual threads, you can think of a Java construct, a Java method, sorry, Java object. It's entirely Java construct. Operating system doesn't know about virtual thread. Operating system only knows about the native thread, right? So what happens is we have already a ability to create native threads, and we have scheduler, which is like fork join pull, which was introduced in Java 7. So fork join pull is amazing thing. We can give tasks to it and it can execute, right? We can get a number of tasks, and it use all the CPU available in our machines, all the cores available, and it's it does in a way so that we don't have it localize information to particular cores, and also it prevents like cache it just makes performant, and because it has own set of what we see. So essentially, any executors that we see, it's they have a blocking queue on top of it, right? So when we submit a task, all this task goes to a blocking queue, and there, let's say I have 10 thread in this virtual in these executors. All those thread pick work from this blocking queue. So if we have one blocking queue, that means there would be some contention, or all eight, let's say if we have 18 in the executors, all eight is going to pull work, right? So if one thread is currently pulling in work from the blocking queue, other has to wait until he removes his lock. So the for example, what it does is it has let's say if we have eight threads in the for example, they will have a eight queue. So the work are pretty much localized. So each thread essentially going to pull work from their own queue. So there will be less contention. That means we'll have more performance. So there are certain other things with the for example. It's extremely interesting and really great, API, really great piece of technology. So maybe we can speak about for example in a whole session. So I'm going to stop there. So keep just bottom line is it's a thread pool. It's a name is for example, and it's extremely performant. It creates the number of threads. It creates a number of threads based on the available CPU. If you have in your machine, let's say I have 10 core in this machines, it will probably create 10 threads, and it will keep using all those 10 threads all the time. All right. So next question gets to be what is continuation? So I'm gonna go into that in a minute. So idea is I have a fork thread pool and I have a virtual thread. Let's say I have created a virtual thread, and virtual thread is going to execute it by this fork thread pool, the traditional the way we do, or you can think virtual thread as a task. We give a task to fork thread pool, and fork thread pool allocate a thread to execute that task, and when it's done, it will give it will take another task. But although it seems the same thing, there is an interesting design implementations over here, which I'm going to talk about. Okay, so this is called continuation. So before I talk about continuation, I have a quick demo over here which I would like to show you. Let's see if I have it over here. Okay, which is this is can you see all this code over here? Okay, so I'm gonna ask a questions to you, Mahmoud, and see if you got it, if you get it right. So this is a main method. It doesn't have a lot of code over here. So you can see I've created the continuation scope. Think it is just a traditional Java class. It created an object of it, and then there is another class called continuations. I also created another instance of it, and I pass a lambda expression over here. So essentially, I'm going to execute these three lines over here, and this continuation has a method called run. So if I call this run method, all these three methods are going to be executed. That's the expectation. So what I have did over here, this is C1, this another statement, this another statement which is C2, all of them one by one, right? And over here I have a statement which is system.println and I print start, and then I call continuation.run. So and I have another method over here. I mean another statement over here, and then I call continuation.run again. And over here, I have another statement. So if I execute this program, if I run this over here, what would be the output? Any guesses?
So my guessing would be that if you first you will have start
Right,
because you still haven't run the continuation,
right,
and I guess you will then have the C1 when you yield the scope. I guess you will have to come back,
right.
and then when you start running back, you will have the C2.
Okay. So you are
This is
exactly
if I
right.
understood it correctly.
Yes, you are exactly right. So if I, execute this program, in fact, exactly that way, same way it executes. That's interesting, and you got it right. And you have seen, if you look into this code, this is the interesting bit, which is, I have started so executing this line, right, C1, and then I have called a continuation dot yield. And what this statement essentially does is, so it's an execution, right? We are executing one by one. In execution context, we have a series of line. It executes serially. Interestingly, when I call this method, so what essentially does it, it suspended the execution from here and goes to the in caller, which is over here, right? I'm calling from this line, so it immediately, from this line, it goes over here, come over here and execute this line. And then when I call this continuation dot run again, the general assumption should be, I mean, if it is a simple method call, it should start from the beginning, right? If you call a new method every time, it start from the top and then end and in the bottom. In the middle, if there is an exception happens, although the execution gets gets to break, but when I call a method again, it start from the top. But over here, it didn't. It start from like the position it got suspended right after that. So it executed this line. So that's an interesting uh, bit of information. So what happens is, virtual thread is basically created by this interesting concept which is called continuation. So let's say, I have um, a, a virtual thread running on a thread, on a native thread, and over here I execute a piece of code and then I call it sleep method. Let's say thread.sleep, right? It's a sleep method. It's a blocking operation, right? It's a blocking operation. In traditional thread, this will block the thread that it's executing currently. And there are other blocking operation. For example, if you need to do an IO, right? If you need to call a network operation is essentially an IO. I'm just writing it over here, network operation. So in our traditional web applications, we call this, especially modern web application needs to call a lot of third-party service, and we are era of microservice. One service basically accumulates result from different microservices. And when we make a network operation, let's say I'm from a thread, I'm calling a network operation. Essentially, I'm waiting to get the result, right? Until I get the result, I'm just staying idle. I'm just wasting my CPU, or I'm just wasting the resources, which is I have a thread, right? And thread is just blocked. This thread is not doing anything else. So that's a blocking operation. And now let's say I have 100 threads available uh, in our applications. That's the maximum number of thread I can allocate, and I have 100. And one thread goes on a network call, and this network call takes like, let's say for the sake of argument, 200 millisecond. And this thread essentially does nothing. It calls the network operation and waits for the result, and network takes 200 millisecond to get the result, to send the result. And this 200 millisecond, this thread is basically blocked. This thread doesn't do anything. It just is there. But in for applications, I have now one less thread to do all sort of other things, right? Now I have only 99 because one thread is basically waiting for something else. Similarly, if you have similar 100 requests, that means 100 of them are waiting from a third party service or network call, and they're not doing anything. They're just idle sitting there, in and since all of them are occupied, I don't have any other thread to execute other program. So I'm essentially blocked. And when I'm blocked, I'm not making any progress. I'm just wasting my CPU. I'm wasting my scarce resources. So that's the problem. So what happens is, in virtual thread, what it does is, whenever there is a blocking operation, it could be sleep, it could be IO, network operation, it yield the execution. It suspended itself. So now let's say I have a virtual thread, I'm calling an IO operation, and I got a blocking operation. I will suspend myself, and I'll get away from the executions, so that another virtual thread take that place and do other things. So that means, although in, for example, I have, let's say, 10 native thread, and continuously I'm getting a lot of virtual thread to be executed, and whenever a virtual thread gets an IO operation, it gets suspended. Another virtual get a chance, there is an IO operation, it gets suspended. So that's how these 9 or 10 threads, if we have a 9 or 10 core available in our machine, always continuously running, and they are using its whole potential. But the virtual threads are basically coming into that for example, and executing a portion of it. If there is a blocking operation, it goes away, it suspends itself. It is resumed later when his data is available from the network operation, right? So these native thread are not basically wasting, or not they are not idle. They are always continuously running, and we are using our CPU like 100%, and we are creating a lots of virtual thread. They are staying on the heap. That's fine. They are not wasting my CPU. They're just suspended. Their execution is suspended. When there is a result in, to them, they will come again. They will execute rest of the code and get done with it. And once the task is done, virtual thread will be garbage collected. That's the highlight. That's the bottom line of this interesting concept. All right. So yeah, that's it. That's all about virtual thread. So let me know if you have any questions.
And Bazlur, how does it exactly yield? Like I didn't see in the. It's a bit still like kind of weird to me that it printed the main thread in the example that you showed. It's like no virtual threads got involved. How did it exactly suspend the execution and realize that it should continue from? I know
Okay.
that it's expected to work like that, but
Okay. Sure. I can perhaps share. Okay. So sure. So let me give you an example over here. So there is a thread.sleep method over here. I can give you. Sorry. So if I go into this method, and so over here, so sleep is essentially a blocking operation, right? If we if we're in a thread, let's say um, this is a virtual thread. Let's forget it. Um, this is also virtual thread. So if I call a sleep method over here, from this line to this line, it's going to be executed by a main thread, right? We know that. So if we call this a sleep method, um, it will just block this thread for a while. Let's say the amount of time we provide. Now there is a new block of code added over here, which is, if it's instead of a virtual thread, we do things differently. So if we go into sleep nanos, there is certain other things where there is a few things called event and other things. So we're not going into all those details, but I'm just going to give you a highlight, which is over here, do sleep nanos. And if we go over here, we'll see park nanos, do park nanos. So you can see over here what is it does is yield continuation for a particular period of time. And now that this virtual thread is basically yielded from the executions for a particular time, there are other things available in this code, right? Called events. Different type of events, different type of interruptions happens. So let's say it calls a network operation. This particular thread is virtual thread is suspended when there is a data available to the socket. There will be some event going on, right? There will be some event will be um, you know event will be generated, and those event will wake this virtual thread again, come to this front that okay, I have got this result. Now we can proceed the proceed the executions. So to accommodate those virtual thread, there are certain especially IO, all those IO API are rewritten, and they are some internals has been changed so that they can accommodate virtual thread. But the idea is that, so when we're gonna virtual thread, you can the highlight is it when virtual thread sees a blocking operation. It can be any IO operation. It will suspend itself, and the IO is going to happen from outside of this virtual thread. I mean outside of this, because IO is dependent, right? My thread doesn't do the IO operation. Let's say I'm calling an IO network operations. So I'm just waiting. So what essentially it does is it's remove this waiting period from this thread. So it encapsulates all this thing inside the virtual thread and removes the execution from the native threads, which essentially executing the virtual thread. And since this virtual thread is removed from this execution, other virtual thread or other work can take this place and continue the execution. So native thread is always busy, and virtual thread is is suspended for a period of time. So there is an example that I can give you over here that will probably give you an idea, which is you can think about it's an analogy basically. It will give you an example, give you a picture over here, which is think about a bank with fixed number of tellers, right? So in terms of Java, teller is like a platform thread or native thread. So when you go to the so let's say you need a service, you go to the bank, and to process your task it requires like certain times. So let's say 5 minutes on average. So traditionally, you talk to a teller and he will ask certain things. For example, your phone number. He probably needs to send emails, then wait for result. While he is doing all of those things, you are waiting there, and teller is also waiting for those results. And in this time period, no other work is done. Right? This teller is basically busy with you, and most of the time the teller is waiting for nothing, and that's it. So so that means if we have like 1 hour window, it will serve only a few amount of customer. On the other hand, think about the other example. Let's say you go to the teller, and teller see your request, and this is what you need to do, and he find out that he needs to make a call or send an email. So when he send an email, he needs to wait to get the result, right? So what he would do is he can ask you that I send you an email. It takes time. It will take some times to get result. Why not you sit on the aisle? I mean, why not sit on the bench and wait for it? When there will be an email, I'll call you and you will come here. Meanwhile, I can serve other customer, right? So that's where we can serve more users, and those user needs to wait. They can wait on a bench and sit and do something else. So that's the idea basically. I'm not sure if I'm able to if I was able to answer your questions. If you have more, let me know. Sorry, you were muted.
Sorry. Yeah, I was saying that it sounds like I read somewhere that it's a little bit similar to also virtual memory, how is it implemented. So, but yeah, it's a great analogy that the one that you gave. I personally liked it, the one about the tellers and the banks.
So similar concepts are introduced in some other programming language. For example, Kotlin, Coroutine, async wait in JavaScript, Python generator, Ruby's Fiber. All those programming languages introduced the similar concept earlier. Finally, it is in the Java as well. So now that there's certain benefits over here, which is that means virtual thread don't consume CPU while they are sleeping, they are waiting or something like that. And technically you can create millions of them in our memory. They're not they're not consuming CPU cycle while they're waiting. So that means let's say I'm just trying to give you an interesting example. Let's say I have a virtual thread, start virtual thread, and let's say I need to do a certain works 8 hours later. So thread sleep time in it hours, sleep 8. I can make, and then I'll do certain things over here. My awesome work. So this virtual thread is can sleep 8 hours without consuming any CPU, and then after 8 hours it can start, and you can resume and do my work. But traditionally, if you want to sleep on 8 hours on a traditional thread, this traditional thread will be idle for 8 hours, and it will not be able to do anything else. It will just stay idle. So that's an interesting contrast. All right. So I have a few demos which I'm gonna share you to give you a concrete example, more concrete example. All right. So there are certain benefits which I'm gonna talk about in a minute. Let me go into demo. Mm, So there is a interesting demo over here. Perhaps I can run it. Okay. What I'm gonna do is I'm gonna remove this folder because I have already downloaded a lot of images. So I'm gonna create another folder over here. Okay. So what essentially is it's created it download random images from web, from a website. So I have two methods over here, which is download with thread pool, traditional threads, and download with virtual threads. So I'm gonna run first of all. I can run both of them at the same time and see the result. So download with thread pool. So over here you can see it's not a fancy code. It just click on this thread, it just goes away and download this image and save into local file. So over here, let's say I have 100 threads, right? That means inside a loop over here, I'm submitting save image method. Save image method basically goes into these locations and pull the information and save over here. So that nothing fancy. So although inside I'm loop, I'm submitting at a point of time all of them. Let's say I have over here 1,000 URL. So I'm submitting as a form of task to this thread pool. But at a point of time, it can handle only 100 requests at a point of time because I have only 100 threads, right? And when I'm sending hundreds requests at a point of time, and since it's an I operation, all of these threads are going to wait to get until they they have the result. Once they have the result, they will save it and then throws another 100 requests to the to the third party service. So and then we'll get a result. Over here, what I did is I definitely calculate the time how much it can take. So we get an idea. And then over here, I did the same thing, which is using the virtual thread per executors. similar stuff. Over here, we just don't have a limitation of how many threads we can use. I'm not sure if I can run it, but let me try it anyway. So I have thousands, thousands over here, thousands, URL. So let's see if I can run it. It will take some times, uh, okay. So it looks like it took a similar amount of time. The reason probably my computer is super busy with a lot of things, a lot of I operations, but uh, I did without any interest of anything running on my computer, and I got amazing result over here, which is
Yeah, probably because of the streaming.
yeah, probably because of this stream.
Yeah.
Yeah, that makes sense. But I have got amazing result. For example, I have written over here thousands, which is um, for 100 threads, it took like this amount of time, and then with the virtual thread it took less than that. So we can I can give that code away and you can try out. And there is another way you can test it though, which is let me see if I can try that. Just give me a second. I'm just finding the code that or maybe I can just share this code base with you all. You can try out. So bottom line is, the benefit of virtual thread is basically, I can just explain a bit over here. So with this virtual thread, we get we submit a task to virtual thread. It goes, goes to um, you know, fetch the image. It's a network call. It requires waiting, so that means it's a blocking operation. It yields itself, and we get another virtual thread, and it also calls continuously. So if it takes 200 milliseconds, 200 milliseconds, no one is waiting for this 200 milliseconds. My computer, my CPU is basically working on other tasks. I mean, sending other requests, other URL. So essentially it's going to send 100 requests at a burst, because no one is waiting. They're just executing 100 line of code is simple, right? It can do in lightning fast way. So it will send those 100,000 requests in a lightning fast, and all this virtual thread, they are just waiting outside. And or the classical, I mean, the fork join pool is basically now free, and it can do other things. So that's the idea. All right. So now look at the benefits. Mm, Again, threads becomes super cheap. We need not to worry about it, and we can again increase the throughput by our traditional request per thread style model in server side programming. And we don't need to use a fancy thread pool. That means we don't need a lot of maintenance, which is tuning up a thread pool is essentially a huge task. And on a blocking IO, virtual thread gets automatically suspended, like we said. So that's awesome thing. And since we can create a millions of threads, that means we can achieve more throughputs theoretically. And probably there's a discussion going on, which is if we need a reactive programming anymore or not. But I'm not sure yet. There is certain aspect, definitely. I mean, reactive programming has a lot of other things. um, Probably those are still important, but at least for the sense of blocking operation, that's our problem, right? Blocking is our enemy. We block our thread, and that's a problem. And since we blocking is not a problem anymore, so maybe if we want to do reactive programming only for this blocking thing, probably you are not going to go, reactive programming way, because it takes reactive programming has a learning curve, and not just reactive programming. Even if you want to do asynchronous programming, it's not straightforward as well, right? It takes certain, cognitive, uh, capacity to understand. It increases the cognitive load, definitely. And yeah, so we can use other things as well. For example, the traditional IO, input stream, output stream reader, we can use them easily now, because I mean, we have been using channel buffer, which are great, but they are difficult to write. NIO is definitely great, but it's not straightforward API. We need to learn it. There is a learning curve, and there is a, there is many ways you can make it, mistake. So those are things. And there is an example over here. So similar example like I showed in this demo. So this is the asynchronous way of doing same thing. This is a, traditional imperative programming. So if I want to explain this code to a junior developer, I'll probably be able to easily explain this the right side of the code, which is, it's a straightforward, imperative code. But the left side, it definitely requires some prerequisites. He has to know, or she has to know, functional programming, compositions, and asynchronous things, a lot of other things, right? So it definitely requires more mental energy over here. So now that we have virtual thread, you can write our traditional way, which is traditional imperative code, and it doesn't require a lot of cognitive load, and we can maintain code better. So these are the benefits. So there are other benefits. Um, so now that the, the demo didn't really work, but you can definitely try it out. I will definitely share the source code and the slides, also the, you know GitHub link. All of them are available in my GitHub, so you can try out. Okay, so I already discussed this. So I have also explained this analogy. I wanted to share it later, but since you asked the questions. So yeah, there's another benefit, which is it's open door for a structured concurrency, but probably I'll not be able to explain or discuss this today, because it will require an hour. So I'll skip that for another sessions. But that's all I had for today's presentations. But yeah, there are certain limitations of virtual thread as well. For example, you are not supposed to do CPU intensive work in virtual thread, uh, because if you need to CPU intensive work, you are going to use the traditional threads, because CPU intensive work doesn't block, right? They keep working. So why need you virtual thread for that? And virtual thread only works well when you have a blocking scenario. So be mindful of that. And yeah, that's that's a good limitations. And there are a few other limitations, which is probably not a limitations, but I just wanted to point out. For example, virtual thread cannot be created using public constructor, which is probably not a limitation. They are not daemon thread, so you cannot turn into a non-daemon thread. Sorry, they are all daemon thread. You cannot turn into a non-daemon thread, and you cannot set priority, definitely. Mm, So virtual threads are part of career thread, so they are not part of any thread group. So you cannot create a thread group, and that's probably a limitations. But who use thread groups anyway nowadays? Okay, so another thing is you should not pull virtual thread. I mean, there is all the pooling concept goes away with the virtual threads. So you want to pull the traditional threads. You are, if you need a CPU intensive work, you are definitely going to use uh, either for joint pull or any other pull. And if you need that, you can definitely pull them. But virtual thread, no, you are not going to do that. So virtual threads are meant to single task only. If you have a single task, you will give it to virtual thread, and That's it. Virtual thread will execute that single task and goes away from the picture, and GC will take care of that virtual thread. And all these, so now that this this virtual thread, it's a Java construct, it's a Java object. They allocate memory from the heap, not the stack. So there's a debate which is better. Stack is outside of the heap, and heap. And if we allocate a memory inside heap, that means a lot of memory inside heap. That means we need to a lot of GC activity to remove virtual threads. So those are trade-off. But if you have, essentially, in the end of the day, if you have a lot of IO activity on your application, for example, or traditional web applications, you see the whole picture, you'll probably see the benefits. But for a simple use case, you will probably not see a lot of benefits. But essentially, the idea is when you have a lot of work, a lot of IO activity, you'll definitely be able to measure the benefits. So there are certain resources over here that I would like to share. You can definitely look into those and get more information about it. I only sketch the surface. It's a huge topic, and it's really interesting how deep you can go. Definitely, so you can look into those things. I'm still constantly learning this topic, and I'm definitely fascinated about the aspect. All right, so that's all I have. Thank you. And if you want to ask me questions later, feel free to reach out to me on my Twitter account. I usually try to respond as immediately as I can. So feel free to uh, reach out through my Twitter. So Mahmoud, that's all I had.
Yeah, so I know that some people probably have missed this presentation. So yeah, don't hesitate if you have any questions to reach out by Twitter or whatever means to ask Bazlur on this wonderful topic. And yeah, I know that Java 19 will be released in very soon, right, Bazlur? It's going to be September this year.
Right.
So it sounds like Java is going to get like a massive at least for preview features, performance for some concurrent code
Right.
with this very anticipated feature of virtual threads. So yeah, this is something to look forward. Um, so yeah, thank you so much, Bazlur, for this wonderful presentation. I don't think we have questions. So, but yeah, like I said, you have Bazlur's Twitter. You can feel free to connect with him and DM with him. Uh, and yeah, we'll get back, I guess, with the slides and the code, the demo that you can run on your own. And this, I have to say that it really intrigued me to find out more about this whole topic. And of course, I see that you have a lot of content about concurrent programming. So would be happy to also have other sessions to cover those as well in
Sure.
the future.
So yeah, I am fascinated about this concurrency thing. So I've been working. In fact, I'm creating some content on concurrency so that it's become easier. I mean, I understand concurrency is a difficult topic, and a lot of uh, developers afraid of it. I was, in fact, I am also even now, but I wanted to try it anyway. So I'm trying to create some content on concurrency. If you go to the, let me share the
Yeah, sure, go ahead.
um, you know resource. So that's over here. So let me see if I can. So over here you can see, I have a 14 that's the series I'm writing. It's the last one is 14. The 15 is going to publish soon. So I'm constantly writing about concurrency. So I started with the basic stuff, and gradually I'll move into more advanced stuff. So if you want to follow, feel free to um, follow this article. You will hopefully you will get some benefits. And if you need to reach out to me, that's my Twitter. You can definitely follow me, or you can reach out to me if you want. And there's also a newsletter that I try to write. It's I'm not frequent, but I'm trying to. So if you want to get to know what I'm doing, or what are the contents I'm writing or reading, you know you can also um, subscribe to my newsletter as well. That would be easier. At least in a month you'll get something from me. Mm, and yeah, that's all I have. Thank you, Mahmoud, for hosting me. And I definitely
Our
want to
pleasure.
definitely want to visit someday in Beirut. And I have heard a lot of good things about your place. And yeah, it's a historical
Thank
place.
you.
There are a lot of interesting things to see and enjoy. I'm looking forward to visit someday in person.
Yeah, sure. Would love to have this in the future. So yeah, there you have it, Bazlur, Java champion. You have a lot of stuff going on around Java, from what I can see. So yeah, quite a lot of good content, newsletters and stuff like that. So yeah, thank you so much for presenting to us, and we look forward to catching up with you again, my friend, in the future. And to those who watched us, thank you very much for tuning in. And of course, you have this YouTube going to be recorded, so you can watch it anytime.
Thank you
Okay,
very much.
thank
Thank you.
you.
Take care.
Have a
Assalamu
good day.
alaikum. Bye bye.
Bye. See you.